Today, in this video, I will be describing the z/OS Workload Manager CPU Dispatching Priority Schema. As you may know, all work in the z/OS operating system is assigned a CPU dispatching priority. And when the z/OS Workload Manager assigns dispatching priorities to work, it uses a set schema or a set sort of layout of possible CPU dispatching priorities. So when you're monitoring your work, it's always useful to understand what that dispatching priority schema is all about. And that's what we're going to be discussing today. Hi there. My name is Peter Enrico of Enterprise Performance Strategies. My team and I are here to help you get great workload performance while optimizing the usage of system resources in the mainframe environment. Our education and our software are geared towards helping you get better performance results and faster. We created the Mainframe Performance channel to help you do what we do. Now, if you're new here, click that subscribe button, and any of the references I give in this video, I'll be sure to link in the references below. So as I said, in this video, I want to discuss with you the CPU dispatching priority schemas that the z/OS Workload Manager has to work with when assigning CPU dispatching priorities. And by the way, when I say schema, I mean sort of the boundaries, sort of the possible CPU dispatching priorities that work can be assigned. So as a reminder, all work in the operating system is assigned a CPU dispatching priority. Now, when I say all work, what am I talking about? I'm talking about address spaces, I'm talking about enclaves. I'm talking about units of work that want to use the CPU. So examples of units of work would be, DB2 thread, batch programs. We're talking about TCBs and SRBs within address spaces that want to actually use the CPU. And those units of work, those things that want to use the CPU, we refer to as dispatchable units of work. So what I'm showing here is an example of the CPU dispatching that happens on the z/OS operating system. The blue squares that we see are representing dispatchable units. These are units of work that are ready to run. They have all the resources they need to run, but now they need the CPU to actually execute the program. And then the circles we see here are the processors. So in this case, I have a 5-way CPU processor for the units of work to want to run on. So as the units of work are wanting to run, they're going to run on the CPUs. But as you can imagine, when the units of work are using the processors, other units of work are coming in, and so we have a buildup of the queue of work waiting to use the CPU. That queue of work waiting to use the CPU needs to be prioritized so that certain work can be placed at the front of the CPU dispatching priority, the front of the queue, other work could be placed at the back of the queue, and then other work could be placed somewhere in the middle of the queue. And that is done through CPU dispatching priorities. So what's happening is, Workload Manager, you assign a workload a goal, you assign an importance level, and as Workload Manager manages that workload, it assigns a CPU dispatching priority, which then dictates how that unit of work will be placed onto the queue, and not so much how the unit of work will be placed onto the queue, but where will that unit of work be placed onto the queue. Will it be placed in the beginning of the queue, the end of the queue, someplace in the middle, and then as work is running, like a typical queue, when the unit of work gets up to the front of the queue, that's where it gets to use the CPU. So in the world of Workload Manager, the possible CPU dispatching priorities are in a fixed schema, and that's what I want to talk about now. So what I'm showing here in this diagram are the possible CPU dispatching priorities that the z/OS Workload Manager can assign work. Now, I haven't mentioned it yet, but I'll talk about it more towards the end of the video, is why would you even care about what the CPU dispatching priority schema is? And the reason is because when you are monitoring goals, when you want to see how effective your goals are, your importance levels are to manage the workloads, or how Workload Manager is managing the workloads, one of the things, or one of the exercises we like doing is understanding, well, what are the dispatching priorities that are being assigned to the work, and does that dispatching priority make sense? So a perfect example I always give is, I don't know how many times I've looked at measurements where customers complain to me, oh, my DB2 workload, it's not performing well. Normally it's doing good, but all of a sudden it's doing poorly. What's going on? And then when we monitor the dispatching priorities, we see DB2 is towards the bottom of the dispatching priority order. And you're like, what is that all about? So the first step to understanding that is to understand this schema in much more detail. And that's why we care about the CPU dispatch and priority schemas. So what you see here is that we have WLM has a set of CPU dispatch and priorities that it can work with. And the dispatching priorities that it can work with range from 191, which is the very bottom of the queue, or the lowest dispatching priority, to 255, which is the highest CPU dispatching priority. Now, at the very top, we see that we have CPU dispatching priority 255 for a WLM-defined service class called system. And I'll talk about system in other videos, but think of the system service class as being certain key address spaces in the operating system that the system cannot even be IPL'd without. That's how important these address spaces are. So what WLM does is give them the highest CPU dispatch and priority and then leaves them alone. The second highest dispatch and priority in the system is for a service class called sysstc, and like system, it has this fixed dispatch and priority, only in this case that dispatch and priority is 254. And work that can go into sysstc is any really sort of address-based oriented work that you classify to the sysstc service class. And I'll get into sysstc in more detail in other videos. And then we have a small range of unused priorities. Don't worry about those. And then we have dispatching priority 248. 248 is sort of an interesting dispatching priority because it's called small consumer. What the small consumer dispatching priority is all about is that WLM sometimes will look at certain service class periods that are running work and see that those service class periods are only consuming just a little bit of work. In other words, the period has work in it, but that work is consuming so little CPU. And sometimes what WLM will do is say, rather than manage that workload and manage the dispatching priorities up and down, I know this workload is only using a little bit of CPU. The CPU consumption is very predictable. Why don't I just put that work into this priority called small consumer towards the top, and then that way when the work wants to run, I know it's going to only use a little bit of CPU, so just give it the CPU, let it do what it needs to do, get off the CPU right away, and nothing really heavy is really running there. So it's a way of just getting the work in and getting the work out right away. WLM will put that small consuming CPU workload into something called small consumer. The next dispatching priorities are really a range of dispatching priorities. And as you can see from the diagram, that ranges from dispatching priority 203 at the bottom all the way up to dispatching priority 247 at the top. It is this range of priorities that I just mentioned, 203 to 247, where work assigned importance levels 1 through 5, or what we say velocity-oriented work, or response time goal-oriented work, that is the range of dispatch and priorities that WLM will use to manage those workloads. So those are the CPU dispatch and priorities you'll see for any velocity or response time goal-oriented work. And then WLM will be managing the workloads within those priorities, and those workloads can go up and down depending upon what the workload is and the goal for the workload and how well that workload is meeting or missing its goal, etc. Then we have another unused priority at 202, so let's not worry about that. And then we have a range of priorities from 192 up to 201 for discretionary work. And this discretionary work runs in what we call a mean time to wait group. So the basic concept of a mean time to wait group is that all work with discretionary will be given one of those dispatch and priorities, and then WLM will spread the discretionary work out amongst those priorities so that the I/O intensive discretionary work will run towards the top of the discretionary range, and the CPU-oriented or the CPU-intensive work will run towards the bottom of the range. And the basic concept here is that when there's enough CPU to get down to discretionary, let the I/O-oriented workloads that are running in discretionary have first access to the CPU. Why? Because we expect them to use a little bit of CPU, and then all of a sudden they're going to do an I/O and go away for a long period of time. So let's just get them in and out right away. And then work that is more CPU intensive, which is the lower priorities, that's the work that will run after the I/O-oriented workloads. And then finally at the bottom here we see dispatch and priority 191, and that's for what we call quiesce work. The basic concept of quiesce is that you can issue an operator command to quiesce or to kind of say to the operating system, I want to stop this work from running. Now, it's a little more difficult to do than just issuing the quiesce command, but the point here is that when you issue what's called the reset quiesce of an address space, that address space is then given the CPU dispatching priority of 191 at the bottom of the dispatching priority. Doesn't mean the work can't use the CPU, it just uses the CPU after all the other work in the dispatching priority schema gets to use the CPU. So basically what we're saying here is it goes to the very back of the queue on a regular basis. So at its core, this is the CPU dispatching priority schema that Workload Manager uses to manage workloads. So as I said, one of the nice exercises to do when you go to revisit goals is you like to sort of verify the CPU dispatching priorities. I'm not saying that work has to have fixed priorities and that this workload always needs to be above this other workload, because WLM will manage things and sort of figure things out. However, what you're interested in monitoring is sort of patterns of activity. So when I tell people, if you're going to do a Workload Manager health check, sometimes what's nice to do is to look at the CPU dispatching priorities and say, hey, relative to the importance level, relative to the goal, relative to what the work is, does the dispatching priority order that Workload Manager assigns to the work, does that dispatching priority order make sense? So for example, here's a small snippet of a day of a particular system that is showing the movement of CPU dispatching priorities. Now I will say this, WLM can change CPU dispatching priorities up to once every 10 seconds. So that's a lot of times it can change dispatching priorities during the day. I'm not saying it changes it all the time, but that's at the most frequent it can actually do so. When WLM changes the dispatching priorities, as you can imagine, sometimes priorities go up, other priorities go down, maybe all the priorities stay the same except for one priority, and that's sort of what we want to see. Now, that discussion itself is a little bit bigger in terms of, does it make sense when something goes up and down? But what I'm suggesting you do for this exercise, for this video, is verify the general order of the dispatching priority. Does it make sense? For example, you have your importance level 1 workloads. Are the importance level 1 workloads towards the top of the dispatching priority range? You have your importance 2 workloads. Are the importance level 2 generally below the importance level 1? Now granted, they could be mixed. You can have importance level 2 above importance level 1, you can have importance level 2 below importance level 3, and they're going to move around. But the general pattern of activity, does it make sense? Or do you see things like, I have this importance level 1 workload, and when the system is really busy, sometimes I see that importance level 1 workload down towards a low CPU dispatching priority. It's those types of patterns that we want to avoid, because that says to me that maybe the goal is too easy, WLM is stealing from the workload, and one of the ways WLM can steal from the workload is by taking that importance level 1, let's say for example, workload, and move it down to a lower priority. Maybe still allow that workload to meet its goal, but now it's running at a lower dispatching priority than maybe you would prefer. And that says to me that maybe the goal is just too easy, that it makes it easy for WLM to steal from. So again, what you can do is, based on certain records, the SMF 99 in this particular example, is plot out the CPU dispatching priorities, look at those dispatching priorities, and just ask yourself, do they make sense? Does the general pattern of activity make sense? Again, don't go crazy if sometimes importance level 2 work is above importance level 1 work. It's the general pattern of activity that you're interested in. And that is the exercise for this video. So, that's it from me, Peter Enrico of Enterprise Performance Strategies. I hope you learned a little bit of something today about Workload Manager and about CPU dispatching priorities. If you have any questions, certainly pop them in the comments below, or as most of you have been doing, is send me an email, and I'll do my best to either answer the email personally or I'll do a video. So give me some recommendations and I'll certainly do a future video. Until then, enjoy the day and hope you're getting great performance. Bye-bye.